let's wait for 5 minutes before we start the session. Okay, so today we will be discussing some problems of given in assignment of week 11 that mainly involves some problems related to the non-linear space. So let's start with our first question. Question number 1. State whether true or false. In fact, all the problems are true false type. State whether true or false. The function defined on Rn, function on Rn defined as this notation is for the function at the point x is mapped to summation I from 1 to n mod xi to the power 1 by 2 whole square, and this happens for every x which is a tuple in Rn as follows. So they're saying that this is a norm. So firstly, let's recall when do we call a function to be a norm. So a function, suppose I denoted something like this, defined on a vector space V to the space of real numbers, is said to be a norm if it satisfies the following conditions, which are firstly, it maps every vector to some positive real number. That means, yeah, norm of x should always be positive, and this happens for every x in V. Secondly, this can be equal to 0 if and only if the vector is the 0 vector. Third one, if K is some element in the field, of course, this is a vector space, so it must be defined on some field. And in fact, mostly when it comes to non-linear space, we consider the field to be either R or C, the set of complex numbers. So if K is some element in field, then the norm of Kx should be equal to mod K times norm x, and this should happen for every x in V and K in F. Fourth one, which is called the triangles inequality, it says that norm x plus y should be less than equal to norm x plus norm y for every x and y vectors in V. So if a function which satisfies these conditions, then we say that this is, yeah, of course, it should be defined on some vector space. If it satisfies these conditions, then we say that this is a norm, and that vector space is called the norm linear space. So for instance, standard norm linear space that you must have read is the space Rn with Euclidean norm. If you remember, we discussed something related to Euclidean norm in the previous session as well. So how is it defined? It is actually defined to be something like this: summation I from 1 to n mod xi square to the power 1 by 2. So the main difference in this and our well-defined norm on this space Rn is the fact that here we have power 1 by 2. So, in fact, this will lead us to some issue, and hence we will be able to show that this is actually not a non-linear space. And the main issue will come at the triangles inequality. So, let's see how that happens. Solution. So, let us check whether this is a norm or not. So, let's go one by one. Firstly, let's see whether it gives a positive value or only for all x. So let x be an element in the space Rn. Then we, by the definition, this is equal to summation I from 1 to n mod xi to the power 1 by 2 whole square. Since we are adding up at the ends positive terms, because this modulus is always positive, so this will always be positive. So first property is holding here. Let's see what happens when norm x is equal to 0. Now this happens, I'll go from on both sides. So let's see. This happens if and only if summation I from 1 to n mod xi square, sorry, xi to the power 1 by 2 whole square. This is equal to 0. That's the basic definition. And this happens if and only if, of course, square of some real number is 0. That means that number is 0 itself. Xi to the power 1 by 2 is 0. Now this is a sum of, this is addition of some positive real numbers, and that is turning out to be 0. This is possible only if all of the terms were actually 0. Because of course we all know that if we add up some positive real numbers, they will give us again a positive real number. So getting 0 in that case is possible only if all the terms, in fact, yeah, all the terms were actually 0. Now, since again, square root of some real number is 0 if and only if that number is 0, and modulus is 0 if and only if that number is 0. This implies that means x is equal to 0. Therefore, what do we get? We get that this is equal to 0 if and only if x is equal to 0. Hence, the second property also holds. In fact, you can see yourself that the third property will also satisfy. Uh, then and x belongs to Rn kx. Now, what does this kx means? We are just scalar multiplying the terms with k with the each component. So this is 1 to n kxi to the power 1 by 2 whole square. Of course, mod k will get outside and we will be left with this is 1 by 2. So that means all three properties holds. The issue comes at the triangles inequality. So I'm saying that this does not hold. That means I should be able to provide you some example such that the property, this, should not hold. I'll show you giving one example. In fact, you can also what do we say? You can also think of some other values for x and y where this triangle's inequality is not satisfied. So the idea is to take terms which are less than 1, because we all know that, well, we take square root of some real number. If that number is greater than 1, that means if suppose alpha is some greater than 1, we know that root alpha will always be lesser than alpha. But on the contrary, if alpha is less than 1, in that case, root alpha will be greater than alpha. So that's where the problem comes. So that gave us some hint that we might take some values which are lesser than 1, so in order to get some contradiction, because if we had this instead of 1 by 2, if we had square, we all know that this is the Euclidean norm and this will form norm. So the issue should come due to this power half. So let's see. Yeah, if I take, now suppose this n is 2, just let's for easy example start with n equals to 2. Take x to be the vector 1 by 16 1 and y to be the vector 1 by 4 0. Let's see how we'll get the contradiction here. So here, what will be x plus y? That means x plus y will be 1 by 16 plus 1 by 4 comma 1. So this is just 5 by 16 comma. So this implies norm x by definition, which is so power half of 1 by 16 will be 1 by 4 and power half of 1 will be 1 whole square. So this is just 5 by 4 whole square. Yeah. Or this is 25 by 16. Okay. And what will be norm of? Yeah, instead I should not call it norm. So value of 1 y will be, this is, so square root of 1 by 4 is 1 by 2, and that of 0 is 0 whole square. So this is 1 by 4. So this gives us 25 by 16 plus 1 by 4. So this will be, yeah, 25 by 16 plus, yeah. Huh. 25 plus 4 by 16. So yeah, 29 by 16. And what will be norm of, again, I should not call it norm. If so the value of x plus y, that will be square root of 5 by square root of 16, 4 plus root of 1, 1 whole square. So this is equal to, just taking the, this is root 5 plus 4 whole square by 16. So let us see which one is bigger. Here, in fact, I can write it. Just use the property a plus b whole square. So this will be 5 plus 16 plus 8 root 5 by 16. So that will be 21. What happened? 21 plus 8 root 5 by 16. Now, since we all know that root 5 is greater than 1, you can in fact find its exact value. It will be obviously greater than 2, because 5 is greater than 4, 4 root is 2. So this will be strictly greater than 21 plus 8 by 16. Why? Because root 5 is greater than 1. So 8 times root 5 will be greater than 8. Now this is 29 by 16, which was, that means, what do get? What do we get? We actually got the reverse of the triangle's inequality. Instead of less than equal to, we got strictly greater than. Therefore, this can never be a no. In fact, on any other. So I hope you understood how we got the contradiction. In fact, it would be good if it will be a very good exercise if you could bring up your own examples. So therefore, the given statement is false. I hope the solution is fine with everyone. If you have any doubt at any step, please let me know. We can discuss it again. I'll wait for 4 to 5 minutes. If you have any doubt, you can ask. Okay, so if there is no doubt, we can move to next problem. Question number 2. Again, a true false. State whether true or false. Let let fn function from R to R with n being natural number be such that this mod fnx is less than equal to 1 by n e to the power minus x squared for every n in z plus and x in R, then the sequence Fn converges uniformly to zero function. We are given a sequence of function and we need to see whether this converges uniformly to this zero function or not. So while looking for the uniform limit, firstly we should know whether it converges pointwise or not. So let's find its pointwise limit. Let x naught belonging to R be fixed. For a fixed x in R, what do we have? We consider the sequence yn to be fn at x naught. If I mark this as first, so by first mod yn, which is actually mod fn x naught, and by equation first, this is less than equal to 1 by n e to the power minus x naught square, because that happens for every x in R. So that means minus 1 by n e to the power minus x naught square. This is less than equal to yn less than equal to 1 by n e to the power minus x naught square. Now e to the power minus x naught square is just a constant and it is being multiplied by 1 by n. So we all know that the sequence 1 by n converges to 0 as n tends to infinity. So now we'll be using the sandwich theorem. Now since this minus 1 by n e to the power minus x naught square, the sequence goes to 0 as n tends to infinity, and the sequence 1 by n e to the power minus x naught square, this also converges to 0 as n tends to infinity. This implies by sandwich or the squeeze theorem, both are same. Squeeze theorem, the in between sequence, the sequence which is in between two sequences which are converging to the same limit, converges to the same limit. We get yn converges to 0. That is, the sequence fnx naught converges to 0. Now, since x naught was taken arbitrarily, I could take x naught to be any real number because this inequality first holds for every x in R. Eventually, we'll get the same thing. Therefore, x naught belonging to R was chosen arbitrarily. This implies fnx converges to 0 for every x in R. Now, if I define a function, what we call the zero function, f from R to R, fx is equal to 0 for every x in R. So by 2, what do we get? We get that the sequence fnx converges to fx for every x in R. That means this function f is actually the pointwise limit of the sequence. That is, we can say that fn converges to f pointwise. Now next we need to see whether it converges uniformly as well or not. So for that, I would like you to recall when do we say that a sequence of functions converges to a function uniformly. Suppose, so this is just something that I want to recall. Suppose this Gn is a sequence of functions. We say Gn converges to G uniformly if the following holds. Firstly, Gnx converges to Gx for every x in whatever the domain of the function is. Or we say that this Gn converges to G pointwise. And the second condition is what we call the sup norm. Gn minus G, the sup norm, which is defined as supremum mod Gnx minus. So if we consider x to be the domain, Gx, for every x in capital X. Now this sequence, now you can see that Yn equals to norm Gn minus G. Now this is a sequence completely dependent on n. It's independent of x because we are taking supremum over all x. This should converge to 0 as n tends to infinity. So if these two conditions holds, then we say that the sequence of functions Gn converges uniformly to the function G. Now above, in our problem, we have seen that the sequence fn converges pointwise to the function f. So that means our condition A is satisfied. Next, we need to see whether this sup norm converges to 0 in this case as well or not. So for that, let's see. I hope this is clear how we say that a sequence of functions converges uniformly to some function. So now this fn minus f sup norm, this is equal to supremum mod fnx minus fx, and in our case the domain is set of real numbers. So which is actually equal to supremum of mod fnx because fx is just 0 for every x in I. So all we need to see is what if the supremum of these functions fn's goes to 0 or not. So by first we have mod fnx less than equal to 1 by n e to the power minus x square for every x in R. Now since this minus x square is less than equal to 0 for every x in R, because x square is always positive. Taking square of a real number is always positive, so minus x square will always be negative. Now we know that the exponential function is an increasing function. This tells us that e to the power minus x square will be less than equal to e to the power 0, which is actually equal to 1. And this will happen for every x in R. Now this tells us that mod fnx, which was lesser than equal to 1 by n e to the power minus x square, will be less than equal to 1 by n, and this will happen for every x in R. That means, now since fnx is less than equal to 1 by n, no matter what the x is, that means our supremum, if I take supremum x in R mod fnx, this will also be less than equal to n. That gives us the sup norm fn minus f infinity, which was actually equal to supremum x in R mod fn x. Now this is less than equal to 1 by n. That means the sequence sup norm of fn minus f is actually in between minus 1 by n and 1 by n. Minus 1 by n is less than equal to, in fact, no need to take minus 1 by n, because we all know that this is a positive entity. This will always be positive because we are taking supremum over modulus of some values. So this is 0 less than equal to, what happened? 0 less than equal to fn minus f less than equal to 1 by n. Then again by sandwich theorem or the squeeze theorem, because 1 by the sequence 1 by n converges to 0. This goes to 0, this goes to 0. Then by sandwich theorem, whatever name you prefer, sandwich or squeeze theorem, we get norm fn minus f, the sup norm of fn minus f goes to 0 as n tends to infinity. And hence, we say that the sequence fn converges to f uniformly. Supplies fn converges to f. And f was what? F was actually the 0 function. No? As n tends to infinity uniformly. And hence, the given statement is true. I hope this is clear. You all understood what the concept of uniform convergence and how the sequence of functions is converging uniformly to the 0 function here. Yeah, I would like you to go through the solution once again. Then, if there is some issue in my solution, and if you have some uh, doubt, you can ask. I'll wait for 5 minutes. Okay, so if there is no doubt, we can move forward. Let's move to question number 3. State whether true or false for a sequence xk in Rn if the one norm goes to 0, then sequence of one norm of xk's goes to 0, then the sequence, instead I write it like this, the sequence of sup norm goes to 0 as well. So firstly, let's understand the notations here. So when we are saying that the sequence is converging to 0, that means this is a sequence of real numbers, because xk norm, one norm gives us a real number, and for each k we are getting a different real number. So eventually we have a sequence of real numbers. So let's see how these are defined. If you can recall, I think we discussed these notations in the previous session as well. So for this xk, now since xk is an element in Rn, that means it is a tuple with n elements. So I can write it as xk1, xk2, so on up till xkn. We have this, the one norm of xk. This is just summation mod xki's, which is xk1 mod plus modulus of xk2, so on up till xkn, which can be written as summation I from 1 to n mod xki. And the sup norm for the same vector in Rn, this will be equal to maximum of all these components. So they are saying that if this sequence, so if I define this, a sequence say yk, which is equal to summation I from 1 to n mod xki for every k in n, they are given that this sequence yk converges to 0. And we need to check that. Now, if we define another sequence zk to be the kth element of the sequence z, is zk is actually maximum of mod xk1 up to mod xkn. We need to check whether this sequence zk converges to 0 or not. So I hope the notations are clear to you. So we need not be disturbed by seeing all these terms, what they are saying. So this is just a sequence of real numbers, and I hope you all must have been very familiar with the sequence of real numbers. So this is just a sequence of real number. You need to see how it is defined, how each term of the sequence is defined. So we'll see whether this zk converges to 0 or not. So we are given that the sequence yk converges to 0. That means we'll use the basic definition. Now since yk, which is equal to summation, or I'll write just the one norm of xk converges to 0, this implies for any epsilon positive there exists a stage k0 in n such that this yk minus 0 is less than epsilon for all k greater than equal to that stage k0, or mod norm xk1 minus 0 is less than epsilon for all k greater than equal to k0. Now, if you remember I think the last problem of previous assignment, there we discussed some relation between this one norm and the sup norm. We will be using that. Now, since the sup norm of xk, this is equal to maximum of xk1, xk2 up till xkn. So obviously this will be equal to some xkj. So that must be less than equal to this sum of, because all the terms are positive and sum of one of these values will be equal to this sup norm. So eventually this will be less than equal to k2 up till mod xkn, which is equal to the xkn norm 1, which is yk. And this was our zk. That means mod zk minus 0, which is equal to mod norm xk minus 0, which is equal to norm xk sup norm, because it's positive and this modulus need not affect anything. Now this is less than equal to, this is less than equal to yk. I mark this as equation by first. In fact, I should mark this one as first and this as second. So this is equal to mod yk minus 0, because yk is positive. And this will be less than epsilon whenever, for all k greater than equal to k0. And this happens by first. Therefore, mod zk minus 0 is less than epsilon for all k greater than equal to k0. And hence, by the definition of limit of the sequence zk converges to 0. That is the xk sup norm. This converges to 0. That was what was asked. So therefore, the given statement is true. I hope this solution is fine with everyone. If you have any doubt, you can ask. I'll wait for 5 to 10 minutes. After that, I think we are left with just two problems. Yeah. If at any step you feel that I have done some mistake, or you're not able to get how we got the next step, because I might be seeing the things from a different point of view and things might be easy for me. But if you have any doubt, you can ask. No need to hesitate. Okay, so if there is no doubt, we can move forward. Next, let's move to question number 4. Again, state whether true or false. If f is a function from R to R is differentiable everywhere, differentiable everywhere, and uniformly continuous, then f dash, the derivative of the function, is bounded. They are saying that if we have a function defined on whole space R, if it is differentiable everywhere and uniformly continuous, then the derivative should also be bounded. But in fact, this is not true. For that, I will give you an example, and I would like you to see if this gives us the contradiction. So suppose if I take this fx to be sine x square. So I would like you to check yourself. Check that right. This function f is actually, I think we did some problem, something like this. I don't remember. I would like you to see whether this is uniformly continuous or not. In fact, this will be uniformly continuous. Just see how f is uniformly continuous. In fact, on whole Rn. On R. Now see whether what can we say about its derivative and its the boundedness of the derivative. Oh, I think I was doing something wrong. This will not be uniformly continuous. No, this will not give us the example. Let's see. Yeah, so a better example would be root mod x. I'll just explain how. Yeah. Consider the function f from R to R, fx to be root mod x. So if you want to plot this function, this will be something like this only. Hmm. And we know that this will be uniformly continuous. Yeah, you can check this one because obviously on any bounded domain it's bound on any closed and bounded domain it's continuous, so it will be uniformly continuous as well. And as extends to infinity, can we say anything? As extends to infinity, yeah, that would be a good exercise. Even I'll have to check. For any bounded domain, not clearly this is uniformly continuous. And when we talk about infinity, we do not know. Okay, I'll define f such that this is equal to root mod x in a bounded domain near zero. And after that, this is some constant. So if we define function to be root mod x from for x between 1 and -1 and 1 outside, this will surely be uniformly continuous. So if we consider f from R to R, fx to be root mod x for, yeah, but we do not know whether but it will not be differentiable at 1 and -1, no? It should be differentiable everywhere and uniformly continuous. Okay, so yeah, this will be uniformly continuous. Uh, so let's do this again. I got confused. Consider f from R to R such that fx equals to mod x to the power 1 by 2. That means mod fx minus fy. This is equal to mod x to the power 1 by 2 minus mod x to the mod y to the power 1 by 2. This will be less than equal to mod x minus y to the power 1 by 2. Why? Because mm, yeah, if this happens, then clearly this will be less than delta to the power 1 by 2. I'll explain that part in detail. Whenever mod x minus y is less than delta, and that would give us uniform continuity, taking epsilon or delta to be delta to be epsilon square. We get that the function is uniformly continuous. So all we need to show is that this mod is less than equal to mod x minus y to the power 1 by 2. So without loss of generality, let's assume without loss of generality, of course, either one of mod x or mod y will be bigger. Then this mod x is equal to mod x plus y minus y, which can be written as mod y plus x minus y. Now by triangles in this will be, by triangles inequality, this will be less than equal to mod y plus mod x minus y, and this will obviously less than equal to obviously be less than equal to plus 2 mod y to the power 1 by 2 mod x minus y to the power 1 by 2. We are just adding some positive term. Now this is equal to mod y to the power 1 by 2 plus mod x minus y to the power 1 by 2 whole square. That means we get this mod x to the power that means mod x to the power 1 by 2, this is less than equal to mod y to the power 1 by 2, just taking square root both the sides, plus mod x minus y to the power 1 by 2. That means mod x to the power 1 by 2 minus mod y to the 1 power 1 by 2 is less than equal to mod x minus y to the power 1 by 2. And since mod x was taken greater than equal to mod y, so taking modulus on the left hand side is exactly same. Mod will be equal to mod x minus 1 by 2 mod y to the power 1 by 2, and this will be less than equal to mod x minus y to the power 1 by 2. Therefore, we get mod fx minus fy. This is less than equal to mod x minus y to the power 1 by 2, which is less than epsilon, whenever mod x minus y is less than delta, where delta is equal to epsilon square. That gives us that this function f is, and this is happening for all xy, so we do not need to worry about the domain. Therefore, f is uniformly continuous, and you can check that it will be differentiable as well everywhere, and its derivative would be 1 by 2 root mod x, which is clearly unbounded. So the derivative is unbounded. Hence, the given statement is false. I hope this is clear how this function is turning out to be uniformly continuous and differentiable everywhere. I would like you to see. I think the only issue of differentiability will be near x equals to 0, but there also you'll get that this function is differentiable. Yeah. So, and but the derivative will be obviously unbounded. So the given statement is false. Please go through the solution again. If you have any doubt, you can ask. We can discuss it. I'll wait for 5 to 10 minutes. We are just left with one problem, which is not that big enough. So yeah, we still have time. You can ask whatever doubts you have. I think I'm doing something wrong in this problem. I would like to go through, see this again. Please don't consider this solution. I think there is still some mistake. I'm confusing somewhere. Uh, if you have any suggestion, you can tell me because either I'm writing the problem incorrect. We'll discuss this problem again in next class. We still are left with one class. I think it's tomorrow. So I'll discuss it again tomorrow. For the time being, let's move to next question. I don't think I did it correctly. Question number 5. State whether true or false. If Fn is a function defined on close AB to R, n belongs to Z plus, are continuous functions, and f is a function from close AB to R, which is Riemann integrable. Riemann integrable such that this integral a to b fn converges to integral a to b f. Then they are saying that the sequence fnx converges to fx for all x in AB, or this fn converges to f pointwise. So for this problem, I'm giving you a hint that the statement is false. I would want like you to look up for some example of the sequence fn such that the integral is converging to integral of some function, but the functions does not converge pointwise to that function. I'll wait for 5 to 10 minutes. Just try to build up a sequence of functions fn which all are continuous and hence integrable, of course, which are the integral is also converging to some integral of some function, but there is no pointwise convergence. Just think. Okay, so let me give you the example. We'll construct a sequence of functions. Consider the sequence of functions fn from 0, 1 to r defined as fn x. This is equal to n square x for x in between 0 and 1 by n. This is equal to 2n minus n square x for 1 by n less than equal to x, strictly less than 2 by n. And this is equal to 0 for 2 by n less than equal to x less than equal to 1. So let's see how does this map, these functions look like. So for n equals to 1, this is equal to fn x is equal to n square x. N is 1, so this is just fx equal fn f1x is just x for all x between close 0 to open 1, and this is equal to 0 for x equal to 1. So if this is 1 and suppose this is 1, so yeah, something like this, open and close. So this will be our f1. What will be f2? F2 will be split 1 by 2, 2 by 2 will be 1, so this is just from 0 to 1 by 2, this will be x by 4. So for at x equals to 1 by 2, so this will be, this should be equal to 2. Yeah, n squared times x, no? So 4x. For x equal to 1 by 2, this will be 1 by 2. After that, this will be something like this. Then similarly, you can see this f3 will be, so this is 1 by 2, will be dividing between 1 by 3 and 2 by 3. So this graph will be something like this, then this and 0. Similarly, this will go on like this. So eventually you can see that as n tends to infinity, the function for all x in between open 0 to 1, this is going to 0. So this implies for x belonging to open 0 to 1, fn x goes to 0 as n tends to infinity. And since of course at x equals to 0, fn x is always 0. So therefore these fn x, this sequence of functions fn x converges pointwise to 0. So now let's look at its integral. So the pointwise limit is 0. But what they were saying that this converges to some integral of some f. So this 0 to 1 fn x dx will be 0 to 1 by n square x plus 1 by n to 2 by n 2n minus n square x plus 0. So that will be, this is just simple integration. You can check that this will be n square x square by 2 0 to 1 plus 2nx minus n square x square by 2, 1 by n to 2 by n. Just put the limits, you'll get that this will be equal to 1. Okay, okay, I'll do the simplification. This will be square by 2, 1 by n square minus 0, plus 2n 2 by n minus 4 n square by n square into 2 minus 2n into 1 by n minus n square by 2n square. So yeah, here this was square. Huh? This will get cancelled out. This will get cancelled out. This is 2 and so on. So this will be eventually just 1 by 2 plus 4 minus 2 minus 2 plus 1 by 2, which is equal to 1. And which is equal to the integral of the function 1. So here the sequence 0 to 1 fn dx converges to 1, which is 0 to 1 1 dx. That means this fx is the constant function 1. But according to the statement, the sequence fn should have converged pointwise to the function 1, to the constant function 1. But it is converging to 0 pointwise. But this fn does not converge to f pointwise. Hence, the given statement is false. This is a very good example. This is a very often asked question. So one should be good with this. If you have any doubt at any step in this question number 5, you can ask. Question number 4, I'll discuss that in next class. I'll wait for 5 minutes. If you have any doubt, you can ask. Okay, so if there is no doubt, we can end this session and we'll meet tomorrow. Tomorrow again we'll have a last session for this course. Thank you so much.